Hello, and welcome to House Call with Dr. Diadamo. I'm your host, Dr. Peter Diadamo. This is episode number 5, entitled The Pancarcinoma Antigen. My special guest this episode is the soon-to-be naturopathic physician, Emily Diadamo, who also just happens to be my daughter. Emily, welcome to the podcast.
Hey, thanks for having me. It's really exciting to be able to be here.
Emily was indirectly responsible for this episode simply because, as part of a homework assignment for her immunology class, she became interested in the topic of today's episode, the Thomsen Friedenreich antigen, a cancer antigen that's found in many, many types of cancers, as we'll soon discover. And Emily, if you want to talk a little bit about how and why you got interested in this particular antigen?
Yeah. So I'm in my second year of school, and I've been trying to keep as broad of an interest web as I can while going through this because I tend to get really obsessed with things, and sometimes things will kind of fall by the wayside. But of course, that's just an intention, and I end up getting obsessed anyways. So I went through this phase where things like modified citrus pectin, larch-arabinogalactan, helix pomatia, glutenin, all these things, and their relevance in cancer immunotherapy just really spiked or piqued my interest. And just kind of working through the logistics of these things, and I'm realizing that they have these commonalities kind of underpinning them. And so talking to you about that and how they shared this Thomsen Friedenreich activity has been particularly exciting for me, and it was a great opportunity for me to write a paper on it in my immunology class.
Well, we're going to delve right into it, but first a moment where we need to just take a step back and remind the listener that this podcast doesn't constitute any sort of patient-provider relationship, and as such, it doesn't constitute medical advice. Matter of fact, if you base your medical decisions on podcasts or internet stories, you may want to rethink that in the first place. But this information is being provided for information and educational entertainment value. Anything that you do that involves treatment for any sort of disease, you should always work in concert with a practitioner who's skilled in the use of these things. And in the case of cancer, that's even much more of a significant requirement. You should obviously have a possible, hopefully a relationship between a conventionally trained oncologist and a practitioner of functional or naturopathic medicine who's got training in providing integrative care in that environment as well. Having said that, I think the topic of today's podcast is quite fascinating since we're coming up with more information that's breaking news about how the revolution in cancer treatments are involving immunotherapy, which I was always taught was something that was a little bit of a lost cause because the notion that cancer cells could be a target for immunotherapy was always thought to be a weak argument because cancer had so many different presentations in terms of the antigens. And in order for the immune system to be involved in any sort of preventive action, there needs to be a focus of whatever the antibody or the particular receptor is for the killer cells. And the theory with cancer was that each cell essentially has its own unique markers, and so there's no real rational way that the immune system can mount a coordinated response. It would have to make an antibody to each individual cell versus an antibody that works across all the different cells. Now, we knew in the past that certain disorders like melanoma had some immunotherapy with them, but melanoma cells are very, very well differentiated. In essence, melanoma cell A looks an awful lot immunologically like melanoma cell B. And when you have that kind of similarity, then an antibody approach makes a lot of sense because the antibody can target a marker that's shared between the cells. But when you get into junk cancers like colon cancer or advanced breast and ovarian, these cells have regressed to the point of almost embryonic characteristics, and they have just markers galore that are just unique to each cell and have kind of defied over the years any approach that involved immunotherapy or immunoaugmentation. However, the interesting thing about our topic is we're going to be talking about an antigen, which we'll get into in a second, what exactly that means, that is shared across a number of very common cancers and represents a possible target for intelligent use of not only conventional treatments, but also there's a surprising number of natural products that are involved with that. So I'm going to just basically turn over to Emily now to go through some of the information that she was able to discover with regard to the biology of what we'll be talking about. And its name has a kind of, kind of an old world charm to it, Thomsen Friedenreich antigen, which typically we call TFA or T antigen. And so essentially, take it away, Emily, and let us know what you discovered about this fascinating molecule.
Sure. So before we even get into this particular antigen and this particular molecule, it's important to kind of underscore what these words mean before we use them. So Thomsen Friedenreich antigen is what we call a pancarcinoma antigen. So breaking that down first to what is an antigen, right? So an antigen is any molecule, whether it's a protein or a sugar, that your body recognizes as foreign and mounts an immune response against it. And I mean, this immune response can be one of a billion options your body has. It can be innate, meaning that it's these kind of, these cells that are at the outside of the periphery. They recognize really something basic that they've seen many times before. They're coded to see, and they mount a response against them. Or it can be what we call adaptive, which is when you have kind of more genetically precise and targeted cells that are mounting this response. So this can be cell-mediated, like we said, which can be kind of a cytotoxic, kill the cell.
And that's usually T cells and things.
It's T-cell
When people hear
mediated.
T cells,
Yep.
or killer cells, you're usually talking about this type of immunity.
Yes, the cytotoxic T cells too, which is an interesting thing because you have on your innate side natural killer cells, which are actually probably our most adept at killing cancer, which they're distantly related to T cells, but they're on that side of things too.
And a lot of what's going on with the new cancer immunotherapy is involving utilizing what are called ligands or binding molecules that are involved in activating a lot of these these targeted killer cells, basically.
And these killer cells are cool because they do two things. First, what they'll do is they kind of bump up against your cells, checking to see that your cell is expressing what we call MHC1. MHC1 is a self molecule that every cell of your own body will express. So killer cells are actually inhibited by cells that present an MHC1, meaning that this is a good guy, we're going to keep him, we're going to leave him.
And MHC1 stands for
Major histocompatibility complex.
Right. It's just like it's a fancy word that says this is me.
And it's also, if you hear about donors or transplantation processes, we'll use the term HLA, which is
human leukocyte antigens.
Yes,
and
but they're actually synonymous. Not technically, but
yeah, they do actually fall normally within
they're
one and the
encoded
other.
by the same.
Give you an idea about the importance of HLAs. I mean, these are the kind of things that are involved in determining whether a person might wind up with an autoimmune disease like rheumatoid arthritis or even whether or not a person has a gluten sensitivity. So what we're learning here is that basically the word antigen means something that elicits a response from something else called an antibody.
Yep, and that's what we call your humoral, so your B cell mediated response. And an antigen can meet an antibody that has a specific receptor that is perfectly fitting to that antigen.
Yeah, very much lock and key.
And it's a really beautiful process because when these two kind of unite to make one, there's a change in that antibody that makes it very, very, very easily perceived by the immune system. So this amounts an immune response. And once those two have met, it'll actually signal your immune system to make tens, thousands more of those antibodies so that the next time you meet that antigen, you're way better prepared.
So when we look at what a pancarcinoma antigen is, we're looking at an antigen that's found across certain types of cancers. And in the case of Thomsen Friedenreich, that cross-cancer antigen expression is, we said before, some of the more common cancers that are seen in the Western world, ovary, breast, colon. There's a few others, right? Isn't stomach, I think, is one?
Stomach. So a carcinoma is really any cancer that originates from an epithelial cell line. So I'd say it's not entirely accurate to say that these are cells that typically line tissues, but it's a good kind of way to think about things. So pancarcinoma means that it's essentially an antigen for all carcinomas.
And for the person who's a true sucker for technical data, I mean, I think that you might want to know that the Thomsen Friedenreich antigen is what is it,
CD176.
CD176, often a derivative of a series of genes known as the MUCs, MUC1, MUC4 are the two biggies. And these are mucin genes. Mucin is a type of a carbohydrate protein, very feathery, and is used oftentimes as a sort of a component of your mucus, amongst other things. And so essentially, like Emily was saying, I mean, these are things that sometimes wind up typically on the surface, and so does a lot of the mucins. And so we're building up a case here that these things are having effects that are playing out oftentimes on the surface with regard to the functions that qualify for making an effective cancer cell, which is the ability to detach and go someplace else, metastasis.
And what's interesting is that this family of mucins, these MUC1 through MUC4s, are most often or very often the first kind of downstream effects of a cell that's lost genomic control. You'll see that what we call aberrant glycosylation, or the faulty application of glycans to cell surface molecules, is one of the first correlates of malignancy.
And the reason for that is, I think, fascinating. These glycans, another kind of important word in this podcast, they're indicating that the compound has certain carbohydrate qualifications. Typically small carbohydrates, sugars, not typically the sugars you would see on a jelly donut, but rather the sugars you would see on cells and on bacteria, the fucoses, the galactoses, and even the blood type sugars are all fall into the category of glycans. The bottom line, though, is that much of the whole glycan universe is based upon the elaboration of these sugars as part of the way the cell communicates with the exterior world, and the way the exterior world actually receives signals and produces feedback to the cell. So I like to think of these glycans as sort of like Sputnik antennas on the outside of the cell that are sort of like feelers. And it's not surprising that when a cell undergoes the process of losing genomic control, as it maybe mutates and has cellular damage from reactive oxygen species or xenobiotics or genomic damage, one of the first things that's going to go is the ability to form effective communications on the outside of the cell.
And that's one of the major underpinnings of what makes tumor so successful oftentimes. It's that it's able to evade the immune system, because the immune system is constantly surveying the periphery for these glycans and to make sure that the expression is what we consider to be acceptable.
And so really one of the major ones is our focus of our talk here, Thomsen Friedenreich antigen, which actually is a glycan that falls sort of into the family of things that are so-called A-like, in the sense that they have structural similarities to the antigen that determines blood group A. A glycan with a rather unamusing name, N-acetylgalactosamine, which basically tells us that it's a galactose-based glycan. And that whole family they're called GalNAcs, that whole family of glycans is involved in a variety of tumor systems, including CA15-3, CA19-9, 27-29. All the common tumor markers typically have some manifestation of the misproduction of a GalNAc molecule. And that probably goes a long way to explaining why I've certainly noticed over the years in clinical practice that whereas the rates of occurrence of cancer between the blood types shows a slight increase of A over the others, it's just so much harder to get the A's into the long-term survivor categories than it is the others.
And why would you say that is? Would you think that's because the body is less likely to mount a response against something that is perceived as similar to self?
Yes. There's a phenomenon in immunology called horror autotoxicus, which means essentially I am in horror of attacking myself. And so the immune system has a fundamental disinclination to want to attack self molecules. Of course, this is used day in and day out by bacterial pathogens who spend most of their time trying to figure out how they can look like you. But the other side of the coin is that cancer cells typically develop a coat of good old A-like, outdoor paint to get out of the cluster that might have been the original body of cells, and then typically try to find their way, if they can, into the bloodstream, and then perhaps past the sentinel nodes and then into the general circulation. And you're going to do that by essentially developing a sort of a cloaking mechanism that would be part of getting past the immune system sentinels. So anyway, we've talked a little bit about the structures and the world of glycobiology, which actually is fascinating because if we look at genomics, we're dealing with 27,000 genes, which may be, if you talk to the ways that the gene can be read, maybe doubles or triples that. So maybe you're talking about 50,000 genes for an average human being. When you talk about the number of different glycans that can be made, it's a much bigger erector set because it isn't really involved in coding for the production of anything. It's involved in communication. And so in essence, the communication that takes place is very delicate. For instance, we know that there was these glycans have, like I said before, they're part of the language of cellular communication. And there was a famous study that was done in the 1980s where they took cells that had a certain residue for a sugar named fucose on a particular part of their antigen structure, and they lopped it off. And these particular cells, these lymphocytes, when they had the fucose in the right place, they went to the liver. But when they lopped off the fucose, they went to the thymus. So a lot of these glycans are like the zip code on an envelope and kind of tells the cell essentially where to geolocate. So we are now basically in the world of A-like cancers and essentially the world of why this would qualify as a pancarcinoma antigen. And I think I want to just kind of talk a little bit about a whole idea of encryption and how that works with the nature of Thomsen Friedenreich. And you I think, have a really fascinating way of portraying that. So I'll turn the microphone over to you with regard to this because it's a very strange world we find ourselves in with this antigen.
It is, when you think about it. And just to make sure that we're on, all of our listeners are on the same page, we've gotten to the point now where we've talked about this Thomsen-Friedenreich antigen being what we call a pancarcinoma antigen, meaning that this is an antigen that's expressed in nearly 90% of all carcinomas. And it actually demonstrates a pretty efficacious way of identifying the presence of carcinomas. Additionally, kind of understanding why Thomsen-Friedenreich would be expressed to begin with comes to understanding what a healthy cell looks like to begin with. So we have, we have this glycocalyx, which is essentially this sugar coating of your cells. It's kind of a candy coating around the cell that allows it to bump into others and to be identified and recognized and signal transduce.
It's funny because if I just interrupt, everybody, when they think of cells, they think of these kind of little blubbery things. You poke them and they're kind of soft.
Yeah, and they have this kind of scaffolding outside of them.
The word calyx comes from the armor coating of an armadillo. It's scales like you would see on a suit of armor. And so we think about these cells as kind of blubbery things, Pillsbury Doughboy, you can kind of push it in and push it out. But it turns out that the average cell is surrounded by a suit of armor that's this structured carbohydrate glycocalyx. And if you want to know a good example of one, just think about the exoskeleton on an insect, because that's a version of a glycocalyx as well.
So let's chip away a bit at the glycocalyx. So underneath the glycocalyx, you'd have all of these antigens, which are normally expressed. And what makes them kind of covert, typically, is they're covered in what's called sialic acid, which is a glycolipid, which is an extremely electronegative molecule, which kind of applies this certain amount of electronegativity, kind of keeping things away from this glycocalyx.
It's sort of like the antennas on the Sputnik. It forces the antennas to stick out, because that's what you want in an antenna, is you want it to protrude.
Exactly.
And if you've ever been to a science center where you put your hand on that ball and your hair, if you have hair, actually extends outwards, then basically you'll know what we're talking about. So we've got this hard armor coating that has some glycans embedded in it, and in the midst of that we have a sea of this more sort of greasier glycan that's around the cell, and it's acting to cause all the things to project outwards. And in that sea is our friend Thomsen Friedenreich.
And an interesting thing just about sialic acid is this is what actually makes the influenza virus particularly virulent, is that it can have different strains of neuraminidase, which is sialic acid.
Right. So when they talk about an H1N1, or an H1N2, they're actually telling you what version of sialic acid the virus is optimized to basically drill through on its way to giving you the flu. So, I mean, we see glycans interacting in the physical world all over the place: microbiome, genomics, pathologies, hormone sensitivity, and in this case, the pancarcinoma component.
And then when we think about what happens with a malignant cell, a lot of the times it loses its ability to add or maintain these sialic acid residues on top of its glycocalyx. So our friend Thomsen Friedenreich, which is typically sialylated or covered, or what we call encrypted, becomes de-encrypted and exposed. This is kind of interesting to think about in this metaphor that you really like to use, and I've definitely become fond of, which is we can consider Thomsen Friedenreich to be akin to a rock, and typically it's covered at high tide, covered by this sialic acid tide. And when it's low tide, that rock becomes uncovered.
So the first thing that a cancer cell loses oftentimes as part of the degeneration of its glycans is the ability to make sufficient amounts of sialic acid to cover up the Thomsen Friedenreich antigen. And it's a good point to understand that this is an antigen that's normally made, it's actually made as part of the cell's structure. You tend to find this antigen on normal cells, but on normal cells, it's covered up like a rock at high tide because the normal cell is capable of making enough sialic acid to cover it, or what we call in medicine to encrypt it, to cover it up.
Which is one of the interesting things because our bodies tend to have at least at the absolute minimum one Thomsen Friedenreich antibody. But typically we have antibodies made to Thomsen Friedenreich, but there's no immunogenicity of the molecule itself because it's what we call encrypted.
It's covered up. It's funny because actually there are precious few antibodies that a normal person makes to their own tissues. It obviously common sense that you don't make antibodies to yourself, right? And the reason that we can make antibodies to the Thomsen Friedenreich antigen as a normal process is because we're not supposed to see it because it's covered up in healthy cells. So here's a tripwire function that makes me think of those old saws we used to say, you know, your body gets cancer every day, but you just get rid of it. Well, here's part of that system because the tripwire is that as soon as the cell starts to become genomically unstable, the sialic acid production gets degraded, which lowers the water in the harbor, which causes, like at low tide, the rock to become exposed, which is Thomsen Friedenreich. So now those antibodies, which normally were minding their own business, can actually attack that antigen because it actually is now identifying that cell is compromised.
And what's
like
interesting...
an early warning system.
Like an early warning system, exactly. And we had kind of alluded to this earlier, but there is this idea that the levels of anti-Thomsen Friedenreich antibodies are lower in type A. And we had said that this is most likely because of this kind of horror autotoxicus, this idea that the body doesn't want to make antibodies to something that it is similar to self.
And if you have Thomsen Friedenreich, which shares structural similarities to type A, it is going to result probably in the production of lower levels of antibodies because your body has feedback mechanisms that say, hey, I'm catching my antibodies up in these other places, and that's not the whole purpose of this system. This system is to go in other words, it's sort of like if you think of the antibodies as the police department and Thomsen Friedenreich as maybe the burglars and the type A cells as people on their way to the library. Well, you don't want the police department to arrest people on their way to the library. You want to arrest the burglars. And so essentially, if you just can't distinguish between people on their way to the library and somebody who's a burglar, you tell your police department to not arrest anybody.
Best to be prudent. So this is of, I would say, a huge amount of utility when we think about ways that we can explore future cancer therapies and look at the kind of historicity of this molecule. I know you have done a lot of work looking into the work of Springer and others. I'd love to hear about that.
Well, I first became aware of George Springer because of his work with blood groups and their presence in biological tissues. For instance, I believe Springer was the person who first discovered that fucose was found in significant amounts in the seaweed bladderwrack, Fucus vesiculosus. He found blood group components in horse amniotic fluid. I mean, this was his work for many, many years. And back in the 1930s and 40s and 50s, this type of serological work was very common. And Springer basically did this work throughout most of his career until, I believe, in the 1980s, his wife developed breast cancer, and then he was spending some time looking at tumor antigens as part of his work in blood group. And he discovered essentially that the T antigen, Thomsen-Friedenreich antigen, might be a really usable place with regard to developing maybe a targeted immunotherapy approach. And the interesting thing here as well is that there's another player who's very important in this story, a gentleman named Gerhard Uhlenbrock at the University of Cologne, who was also a lectin researcher. And it was Gerhard Uhlenbrock who actually discovered the structure of the Thomsen-Friedenreich antigen, believe it or not, by using plant lectins as molecular probes to get the particular glycan structure figured out. Springer kind of worked in the same area and wound up developing a vaccine that was named after himself, Springer vaccine. And that was a combination of certain types of red blood cells that he had treated to actually remove a lot of the sialic acid. So he was getting the sialic acid off for other purposes to get that antigen exposed. And he added some calcium phosphate and made a vaccine out of it. And then he co-administered this with the typhoid vaccine, which I thought was a profoundly astute observation because having been a naturopathic physician, one of the first things you do is read a book called Borchi's Materia Medica. And Borchi had brought my attention to typhoid with regard to certain botanicals that also had some significance as well, which we'll talk to in a minute. But there's a notion here that typhoid acts as a way to sort of trick the immune system into behaving a little bit more aggressively towards Thomsen-Friedenreich. He had discovered that giving typhoid at the same time, the typhoid vaccine, kind of, it sort of tapped the immune system on the shoulder and said, we know you're looking at this, but did you see this thing over here? Because I'm not sure you're paying attention. So it's kind of like a little bit of an education towards the variations in the structure of the T antigen, which we can't go into because it's a lot of molecular biology, but there's a lot of ways your body recognizes things, and a lot of that has to do with the feathery nature of these glycans and branching structures and things that convey ever so slight structural differences but have significant effects as to how your immune system recognizes them. So Springer had discovered that if he gave the typhoid vaccine simultaneously, his vaccine became more promiscuous and had the ability to target a greater range of cells that were expressing Thomsen-Friedenreich.
Of particular importance is this notion that during times of acute infection with certain bacteria, including Salmonella, which is typhoid, we express more Thomsen-Friedenreich antigens, but they tend to clear up and become re-sialylated after we kick its butt.
Yeah, the sialic acid comes back.
It does.
Yeah. Now, it's interesting that actually he wound up making this vaccine. He put it into clinical studies. The vaccine had significant results in women who were even stage 3 and stage 4. And then he died. And that was the end of the Springer vaccine. It was lost in a series of lawsuits between his estate and the University of Chicago for many years. And then by the time they got that all reconciled, nobody was interested in it anymore. The researchers that had originally worked in it had gone on to other things, and he was now deceased. However, it always attracted my attention for two reasons. It fell beautifully into the blood type characterization scheme. It fell beautifully into what we know about the effects of things like lectins, and it gave indicators that there might be natural products that could be used by practitioners to help hot rod this very basic type of defense mechanism. And, essentially, as Emily was saying before, we talked about the typhoid vaccine. And this is a very uncommonly used vaccine typically because people only get it usually when they go to places where there's like poor sanitation and stuff. However, it's extraordinarily safe. It has one of the highest safety profiles of any vaccine, and it's typically given by oral challenge. So in other words, you get 2 or 3 of these little capsules and you take it over a couple of days. And we've advocated that people who were under care be contemplating doing this kind of thing as well because it is such a safe vaccine and it does fit so nicely into the mechanisms that we could exploit in other ways. And I think one of the things that I think attracted Emily to this whole area was that there were some of her favorite botanicals were actually implicated in some of the therapeutics here. So why don't you talk about those, Em?
Sure. So actually, interestingly enough, part of what triggered my interest in this was that I have been fortunate enough to be able to write some of your product descriptions, kind of reformulate them and give them a voice that I love to write. So it's been a great experience. And one of the products I was writing was for Helix, which has Helix pomatia aspersa, either species. I believe one of them is, I know you know the difference.
Aspersia and pomatia.
Mm-hmm. And
Roman snail or burgundy snail.
And which is interesting because they're not even botanicals. These are snails. This is escargot. But these have what we call Helix pomatia agglutinin, which is a lectin that actually can bind to Thomsen Friedenreich.
It can bind Thomsen Friedenreich and quote-unquote A-like tumor markers.
Yes.
And this actually is very significant because there was work done in the actually early 2000s that was reported in The Lancet on a molecule known only as LLC, and that stands for ligand-like complex. And it turned out that this was a marker that the researchers had discovered they were finding on breast cancer cells that was correlating with the capacity of the breast cancer cell to get out of the what they call the sentinel nodes, the regional nodes, which are supposed to act as sort of a roadblock to prevent cells from getting access to the bloodstream and spreading. And as soon as the cell manifested this LLC molecule, it was almost like it was given a passport. And what they discovered was that this LLC molecule actually interacted directly with the lectin from Helix pomatia. Probably even more fascinating to me, because I love history so much, was to find a 15th century medical monograph from Italy that advocated that if women had diseases of the breast, they should be encouraged to eat large amounts of snails.
That's incredible.
Empirical observation. And I always marvel at these types of observations that people just make. We live in our times are too hurried for people to make these kind of observations. You have to live in very slow times where you can see things over and trends that are available. But you think about this kind of observation, and then we put a molecular basis to it. It's mind-blowing.
It is. And having that good eye and seeing what works over time, that's a combination of patience and a good eye, it sounds like. So Helix was of particular interest to me, but also another one was one of my favorites to begin with, which is Baptisia tincturalis, or wild indigo.
Wild indigo.
Which is usually yellow, so not sure why.
I think it has to be. It has to undergo some other types of reactions before it turns purple. Or I'm not sure. I don't think it was really ever used to dye anything. But it's a beautiful plant. I used to grow
beautiful.
it. And it's a perennial, so if you put it in your garden and as an herb, it comes back year after year and just gets bigger.
And it's hardy. It has these great-looking seed pods, so it's just constantly self-fulfilling.
And Baptisia tincturalis had a reputation in the eclectic herbal world as so-called alterative. It falls into the same category as an herb like echinacea. And alterative, you can euphemistically call it almost like a blood cleanser, something that the old days, they figured there was something in your blood you had to get rid of, and these are the herbs you take. And ultimately, Baptisia tincturalis had a reputation on par with echinacea, according to the old eclectic physicians. And it was used a lot for things that the old eclectic doctors thought was the result of having stuff in your blood you shouldn't have, like acne and digestive problems and stuff like that.
Which is interesting because the way that a lot of contemporary naturopaths view Baptisia is that they call it something which we call a lymphagogue, which is something that similarly, but not so similarly, cleans the lymph, which is your major detoxification way. So, it's not too far off. It's just perhaps a different type of circulation.
And Baptisia tincturalis has it has a few alkaloids in it that you have to be a little bit respectful of. Alkaloids are the more medicinal parts of plants you typically see versus flavonoids, which are typically water-soluble and a little bit safer. But the interesting thing brings us back to Boerke's Pocket Materia Medica, where he made this almost offhanded observation that I read many, many years ago, that Baptisia increased the opsonic index against typhoid. An opsonic index is something that people used to use back in the 20s and 30s, where they would actually take your serum and incubate it with some bad boys and see how aggressive your white blood cells were. And that became the opsonic index. In other words, how effective the substance was opsonized. It's an old word that it meant how effective were you able to cover the bad boy with antibodies. And Baptisia basically increased this ability, this opsonizing ability of the body against typhoid. And I thought to myself, reading Springer's work, typhoid, Springer, Baptisia, Springer, typhoid, and away we went. So I've just always been a real big fan of, especially in situations where the situation is such where you've got a type A or an AB, where you really have to do a lot of extra work to get that immune system to really go after things. Baptisia is a key player in what I put together for most people. The other one, I think, is something most people associate with a cough drop.
Horehound.
Yeah.
Marubium vulgaris. And tell me a bit about that, because from what I understand, it seems to be a combination of some synergy, but also perhaps a little bit of some evocative potential.
It does. Marubium has a lectin on its own that seems to be specific for Thomsen Friedenreich. But also, too, a separate study showed that it has some ability to increase the antibodies. So, and think about this. If we have a lectin that's specific for the tumor antigen, that's kind of like a plant antibody in a way, because lectins are attaching to things that are acting as antigens, just like your antibodies are attaching to things. So, of course, nowadays, everybody thinks lectins do only bad things. But if you know your molecular biology, they do all sorts of wonderfully good things, too. And we're going to talk about now two other lectin-containing foods that do all sorts of marvelous things, and they're just so humble. One of them is, we just had it last night for soup, which was awesome. Agaricus bisporus, which is your standard domestic or supermarket silver dollar mushroom, and Vicia fabia, which is, depending on where you live in the world, is known as a broad bean or fava bean. Both of these beans contain lectins that actually have specificity against A-like antigens, such as Thomsen Friedenreich. And the interesting thing about the lectins that are in both of these foods is that they have a high degree of specificity for the more dangerous versions of Thomsen Friedenreich, the ones that are more associated with spreading and all sorts of bad stuff. So these guys are really, really good at being able to latch on to these types of antigens in such a way so that you can get a better response on the part of the immune system, because a lot of times using plant lectins, the lectin gets in there and creates what's known as an immune complex sort of thing. And anytime you glom something up, it starts to have trouble existing in the body. Body likes everything nice and smooth and slippery, and as soon as you start sticking things on things, the body starts to realize over time something's really bad here, and they've got to either get rid of it or detoxify it or disarm it. And so these particular plants, the broad bean, fava bean, and the domestic mushroom, contain lectins. And in the case of the mushroom, talk about a superfood, you have similar Thomsen Friedenreich mechanisms that take place in the colon. And if there's certain genetics in place, you wind up with what are known as colon polyps. And people get a sigmoidoscopy or colonoscopy, they come back and they say they got colon polyps. And I always give them the same advice, which is, okay, they're going to scope you again in 6 to 9 months. So between then and now, you should eat a huge amount of mushrooms and eat a lot of broad beans and stuff like that, and let's see what happens. And they almost always come back later and say, well, they scoped me again and things looked a whole lot better. And the reason being is that not only are these lectins specific for the elaboration of the Thomsen Friedenreich that's coming out of the polyp, but their interaction as a lectin seems to push buttons inside the cell that forces it to go back to a more normal state, which is a whole different thing than an antibody. Antibody just targets something for destruction. These lectins are actually reprogramming the cell to go back to something closer to normal.
Which is interesting when you think about it, because we were kind of talking about the glycomics of cell surface molecules and how there's so much that happens with cell-cell recognition, but a lot of it is signal transduction. So it actually has an internal mechanism when you have either a change or an expression on the cell surface. So it's incredibly intuitive. And to think that this can just only be furthered with food products is marvelous.
And I think at the same time, you're looking at things that are lifestyle adjustments, maybe some targeted botanical medicine under the guidance of a person who's expertly trained in those things. But also, too, these are long homework assignments, too. If you tell a person, here's a desired role that we want to use this food for, but it's going to take some time. But then again, what's the downside of simply increasing your consumption of mushrooms? Mushroom soup, or you have some mushrooms sauteed in some ghee, there's many ways of eating these types of things that are quite enjoyable. And most people say, well, I can certainly do that. And with those kind of things, it's just so simple to be able to accomplish. And, the interesting thing about molecular biology is that sometimes you have enough information about the interactions and the proclivities and the specificities of a receptor and a lectin and a molecule and an antibody. And because you can be so precise in that particular time and place that you use it for that particular reason, sometimes day-to-day ordinary things become magical. And I think it's a very powerful thing here, because that keeps us within the realm of what we like as naturopaths to have a wide margin of safety. That's the most important thing. So this concludes our discourse into this remarkable Pancarcinoma Antigen. It's been a joy to have you here, Emily, and to participate with you in this exploration of just a fascinating area.
Thank you so much. It's been, an honor to even have this privilege just 2 years in, but also this has been so fun. You and I, we love going back to back about these kinds of things, so It's nice to have an outlet for them.
This is a recording of a conversation that probably occurs on our dining room table a couple of times a week.
It certainly
does.
It's
been nice to allow you to the audience to listen in. I hope you come back soon. We'll talk about another topic one of these days that you find interesting in your soiree into naturopathic education. Anyway, this concludes the episode number 5 of Pancarcinoma Antigen. I'm your host, Dr. Peter Diadamo, and my special guest.
I'm Emily Diadamo.
And until next time, again, I'd like to remind you that this material is provided for entertainment and educational purposes. There's no patient-provider relationship that's the result of this, and this does not constitute medical advice. If you'd like to try to explore more about these particular elements, I would suggest you work with somebody trained in their use under the guidance of a trained naturopathic doctor, perhaps in concert with a conventionally trained oncologist. Until next time, be well, and this is House Call. Take care.